All right, so to wrap things up in section 3.2 here, we're going to look at something called the second derivative test. Now, in the previous section, we talked about the first derivative test, and what that was a way of using the first derivative to find where a function had a local maximum or a local minimum value. We looked specifically for those things called critical values, which is where f prime was equal to 0, and then we looked for a change from either increasing to decreasing at that value or decreasing to increasing. And that would tell us if the value that we were looking at was giving us a local maximum or a local minimum, or if neither of those changes occurred, we had neither type of local extremum. We have an alternative to that first derivative test that uses the second derivative, which unsurprisingly is called the second derivative test. And what it does is it uses concavity as a different perspective to determine whether a function gives us a local maximum or local minimum. So for example, let's take this graph right here. You can see that I have a local minimum right here. It's the lowest point on this portion of my graph. It's occurring at this value c right here. So if I was using the first derivative test, I would notice that as I pass through this point where I get this horizontal tangent, that's what we're looking for when we find those critical values. Or at least sometimes. Remember, it can also be where a function fails to be differentiable. But in this case, we have a horizontal tangent, critical value there, and we change from a decreasing part of our graph to an increasing part of our graph. That's what the first derivative would be used for to tell us that this is a local minimum. But another thing worth noticing is that the function is concave up here. Notice we have concave up. So when a function is concave up, that means that the curve is going to take the shape of one of these valleys, which tend to have these low points. So that's the observation that we're going to use in the second derivative test. Notice in this other graph over here, where I have a local maximum right there, again at a critical value where I have a horizontal tangent, this graph is concave down, creating this hilltop of sorts, and it's at the top of that hill that we had our local maximum. So we can use concavity to come to the same conclusions that we came to during the previous section when we did the first derivative test. Here we are summarizing this test that I'm talking about here. Suppose f is twice differentiable at x equals c, that's the value that was showing up here. And suppose x equals c is a critical value of f such that f prime of c equals 0. So we're specifically looking at the type of critical value where our derivative is equal to 0. That's one of these two cases generally. Then if f prime of c is negative, which remember that means f is concave down, then f has a local maximum at x equals c. So that's this case right here. We had a critical value at c where f prime would equal 0 because that's the horizontal tangent that we're seeing. We're concave down, which means f prime at that value would have been negative. That gives me a local maximum, okay? If f prime of c is positive instead, then our function is concave up like we're seeing here, and that would give me a local minimum. Finally, if f prime of c is equal to 0, so it's neither positive nor negative, then the second derivative test fails, and f may have a local maximum, minimum, or neither. So in other words, we can say that if the second derivative of our function is equal to 0 at that critical value, then the second derivative test is inconclusive. Okay? Now, as I mentioned before, the second derivative test is an alternative to the first derivative test. So the first derivative test and the second derivative test both do the same thing. They both tell us whether a value at a critical, or whether a point at a critical value is giving me a local maximum or a local minimum, or potentially neither. And so that means that there's never a case where we have to use both tests. Generally, we get to choose one or the other. And there are certain pros and cons to each test. So notice in the second derivative test, there are a couple of extra conditions that are in place. First of all, the type of critical value that we have has to be one of these types, where f prime of c is equal to 0. It can't be the type where f prime is not defined at c. Remember, that's another type of critical value. The other issue is that if the second derivative at c is equal to 0, then the second derivative test is inconclusive. We don't get any information from it. So those are some shortcomings of the second derivative test. The first derivative test will always work, regardless of what kind of critical value that you're using, and regardless of whether the this won't happen because f prime of c equals 0 is where we get those critical values from in the first place. So the question kind of arises, why would you ever use the second derivative test if it has the potential to fail where this first derivative test does not? And the reason why you might choose the second derivative test instead is because in certain cases, it's actually faster. That seems a little bit counterintuitive because you have to take an additional derivative to get to this test that you did not have to take in the first derivative test. But the trade-off is in the second derivative test, we are not making sign charts. We don't need to plot our critical values on a number line. We don't have to check test points to determine where things are positive or negative. We get to skip all of that. And that was part of the first derivative test that was kind of time consuming. So the second derivative test cuts that extra time out if it works. So let's take a look at an example where we want to use the first derivative or second derivative test. And specifically, we're going to assume that we have a function f that's defined everywhere and that it's twice differentiable. We're going to use the second derivative test to classify whether f has a local min, local max, or neither at each of the following x values. And if it's not possible to make that conclusion, we're going to explain why. So here, notice I'm not given f explicitly, I'm just given some values. Here, for part A, we see that f of 8 is equal to 0. We also see that f prime of 8 is equal to 0, and f double prime of 8 is equal to 120. So I'm using 8 as the x value in each one of these. Do I have enough information here to conclude anything about 8 as far as, what if it gives me a relative extremum and what kind? Well, the fact that f of 8 equals 0 is not going to be useful quite yet. So f prime of 8 equals 0 implies that there is a critical value at x equals 8. So x equals 8 is a critical value. Remember, whenever our first derivative is equal to 0, that's one of the places we get critical values. Specifically, it's the type of critical value that I want to see if I'm going to use the second derivative test. Secondly, I'm not going to write that as and. F double prime of 8 is positive because it's equal to 120, right? So here's what I know. I know that f prime of 8 is a critical value, and I know that my function is concave up at that critical value. That implies that we have a minimum, a local minimum at 8. So we have a local min at x equals 8, and that's because of the second derivative test. That's all I had to verify. Let's try the second part, part B here. What can we say about this? So f of negative 15 is equal to 23. Notice in the previous example, I never used that first fact. Where that would be used is if I identified the fact that we have a local minimum at x equals 8 here in part A, and then the question asked, what is that local minimum? Well, in this case, the local minimum was 0, and it occurred at x equals 8. The problem didn't ask for that, so I never needed to use that first value. The second value, f prime of negative 15 is equal to 0. So f prime of negative 15 being equal to 0 implies that we have a critical value at x equals negative 15, okay? So that critical value could give me a local maximum, it could give me a local minimum, it could give me neither. If I want to apply the second derivative test, I need to now know what happens to f double prime of negative 15, and if it's either positive or negative, I can draw a conclusion from that. But it's neither, it's 0. So f double prime of negative 15 equals 0 implies that the second derivative test is inconclusive. So if I was trying to find local extrema, I would actually need more information about this function, and I would need to use the first derivative test instead because the second derivative test didn't get me anywhere. Okay, let's do one last example where instead of being given just a little bit of information about those functions, we want to apply the second derivative test to functions that we know explicitly. We have algebraic representations for them. So first, to find local extrema using the second derivative test, we're going to use this process. We want to know what the domain of f is. We want to find all critical values of f, specifically if we're going to use the second derivative test, we're going to need f prime of x equals 0. However, since local extrema can occur at places where f prime does not exist, we'll need to make a note of those as well. Because if we can find any of those, we'll have to apply a different test to those. We also need to know if those are in the domain of f to be useful. Finally, we want to find f double prime and evaluate it at all of the critical values where f prime was equal to 0, because that's when we can use the second derivative test. Let's start with part A. F of x is equal to x times the natural log of x. So the first thing I want to do is find my domain. Because the natural log is there, we know that the domain is the set of all positive real numbers. It's that, okay? Now, in order to find critical values, which was step 2 in that process, I want to take the first derivative, so f prime of x. I would need to use my product rule. Derivative of x is 1 times the natural log of x, plus x times the derivative of the natural log of x, which is 1 over x. This simplifies to the natural log of x plus 1. Okay? So here, if I'm going to try and find critical numbers, or critical values, rather, I need to solve this for x. So, solve it for x, but setting it equal to 0 first. Now, I also need to consider where this thing is not defined. It's not defined for any negative real number or 0, because again, we have that natural log. But none of those values are found in the domain of the original function. So even though we have lots, infinitely many really, places where this is undefined, none of them can be critical values because they don't belong to the domain of the original function. Here, if I wanted to solve this for x, I would have the natural log of x equals -1. Take e to the power of both sides, and I get x equals e to the -1 power. So that's the one critical value that I get in this whole thing, okay? Next step, what I want to do is take the second derivative. So what is f double prime of x? Well, we're going to use this representation. Natural log of x is equal to 1 over x when I take its derivative, and then the 1, of course, goes to 0. So what do I want to do now? I want to take my critical value, which we found in the previous step, plug it directly into f double prime. What is f double prime of e to the -1 power? Well, that would be 1 over e to the -1, or just e, right? Because it's the reciprocal of e to the -1, which is already the reciprocal of e. E is a positive number. Remember, it's approximately 2.7 something, something, something. So all we needed was whether this is positive or negative. And again, because the second derivative is positive, our function is concave up, which means we have a local minimum there. So by the second derivative test, f double prime, f has a local minimum of, now we didn't find the local minimum, we just found where it occurs. It occurs at e to the -1. So I'll need to plug that back into my original function f of x there and find what it's equal to in order to state what that local minimum is. So I would say it's equal to e to the -1 times the natural log of e to the -1. Remember, these cancel, and so I'm left with negative e to the -1. So that's kind of the work that I used to get that local minimum. By the second derivative test, f has a local minimum of negative e to the -1 at x equals e to the -1. That's what we plugged in to find it, okay? So I talked through a lot of that, which added some time, but if you notice the steps here, there wasn't that much to do. we found a couple derivatives. From the first derivative, we found a single critical value. From the second derivative, I plugged my critical value in and determined that I had a positive number. Those two facts combined gave me a local minimum, and then I just determined where that local minimum occurred. The first derivative test would have taken more time because I would have needed to create a sign chart. I would have needed to pick test values and determine if we change from increasing to decreasing or vice versa or neither. That would have taken more time. So in cases like this, the second derivative test is actually faster. It's more efficient. Let's try one last problem. F of x is equal to 100 over x plus x, which I can write this way, 100x to the negative 1 power plus x. That makes the derivative easier to do. Okay, so just as before, we want to determine the domain of our function and then determine any critical values and then use our second derivative test to see what happens. The domain of this function is the set of all real numbers except for 0 because I'm dividing by 0 there. So I can write that in interval notation this way, negative infinity to 0, union 0 to infinity. Okay? From there, find your first derivative. F prime of x would equal power rule, negative 100x to the negative 2 power plus 1. Negative 100 x to the negative 2 power plus 1. Okay? Which is the same thing as 1 minus 100 over x squared. So I need to find where this thing is either undefined or is equal to 0. Notice this is only undefined at x equals 0, but x equals 0 cannot be a critical value because that's not also in the domain of the original function. So instead I just want to solve this equation. If I added this over, I'm going to get 1 equals 100, not 1,000, 100 over x squared. If I multiply both sides by x squared, I get x squared equals 100. And then take square roots of both sides. X is equal to plus or minus 10. So it's plus or minus. So you need both solutions from that. Okay? So these are going to be my critical values. Now let's find the second derivative so we can use our second derivative test. So here, I'm going to use this version of my first derivative to take another derivative. The 1 will go to 0, and then I'm going to get positive 200 x to the negative 3rd power, or 200 over x cubed, same thing. Okay? Now, let's see what happens when I take my first and second derivative. So f double prime, let's see what happens when I plug my critical values into that. So f double prime of 10 is equal to 200 over 10 cubed. I don't actually care what that's exactly equal to. It's not hard to find, but remember, all we care about is whether it's positive or negative. So 10 is positive, so 10 cubed would be positive. 200 is positive. I have a positive number divided by a positive number, which is, of course, positive. Now check negative 10. That was the other critical value. That would equal 200 over negative 10 to the 3rd power. Because that power is an odd number, cubing a negative number would remain negative. So I have positive divided by negative, which is negative. In this first case, positive second derivative means we are concave up. Negative second derivative over here means we are concave down. So I have a local min and a local max. Summarizing this, we have a local min of, now what is that local minimum equal to? Well, remember, you have to plug these values back into the original function to determine what that's equal to. So let's do that over here. What is f of 10? Well, remember, f was defined to be 100 over x, so 100 over 10, plus x, which is 10. That's 10 plus 10, or 20. What about f of negative 10? That would be equal to 100 over negative 10 minus 10, which is negative 20. So I have a local minimum of 20 at x equals 10, and I have a local maximum of negative 20 at x equals negative 10. And that's again by the second derivative test. Notice it still took work, but I didn't have to put all of the time into creating a sign chart and doing all that stuff that we do for the first derivative test. So it was more efficient than the first derivative test would have been. Okay, this is going to wrap up 3.2 for us.